Hey everyone, and welcome to the SaaS Developer channel, where we discuss technical aspects of building SaaS products. And welcome to 2023, the beginning of second year of this podcast. I am so excited, and I wish everyone in our community an amazing year. So, last week, I saw Gunnar post a really good question on Twitter. He said, separating storage and compute versus predicate pushdown. I can't quite square these two with each other. Is there a world where they coexist? Or is it just two opposing patterns, opposing trends in database technology? Guys, I love this question so much because there are probably so many developers who are wondering the same thing. And Gunnar was just brave and smart enough to ask. But there are also many developers who probably feel the answer is totally obvious. And the reason is that the word storage and the word compute don't quite mean the same thing to everyone. So let's start in the beginning, where we have a single machine running Postgres. And if I have this one single machine, obviously compute and storage are not separate. I cannot even open this freaking box. But this is not a production machine. The production equivalent will be a machine with some SSDs in it. It used to be common early days of the cloud, etc. Today, in data centers and in the cloud, you typically have a machine that the database is running on, and it's connected to storage. You have a NetApp, EMC, AWS has EBS. Storage is already, for the most part, kind of away from the compute. And important for Gunnar's question, this storage device has compute. It has CPUs. It's not a disk with a network card and cable attached to it. So now that we have a machine running the database and storage that is actually connected to it from another cluster, did we separate compute and storage? In some ways we did. So first of all, compute and storage are essentially different workloads. Machines can be optimized for them, right? So we have the compute nodes, they use CPU for database things, parsing queries, optimizing hash joins. They need tons of memory to do all that. And then the storage nodes use CPU for storage things, encryption, snapshots, replicas, etc. So we already get a bit from separating them and configuring things separately. Second, they fail independently. And you have, because you need different reliability guarantees. Without this separation, if I take this lovely machine and drop it, I've lost the database, I've lost my data, I lost everything. I'm not available, but I also no longer have data, which is worse than just being unavailable. Hopefully I have backups, but depending on a lot of things, it may take a while to recover. So I'm, at the best case, looking at extended unavailability. In the worst case, I did not have backups. If things are decoupled and I lost my compute machine, I'm unavailable, which sucks, but also no big deal. I can spin up a new compute machine, or I can bring up Postgres somewhere, connect it to the same storage device, and I have all my data back. It still takes time to recover, but obviously it's significantly faster to connect to a database already on disk than starting to read from tape and all that stuff. So generally speaking, the reliability of the storage cluster is much more important, and they are built that way. They are built for very, very high reliability, never losing data, etc. Compute cluster, it can be, you can do however you want based on your SLA. Do you need a hot standby? You should have it. Is it actually acceptable to take some lack of availability and bring the database up. It takes maybe, depending on your automation, anything from few seconds to few minutes. Up to you, how you like your SLAs, how you like complexity. It's your needs, but you now have this option, and decoupling gave you this option. So yay, decoupling. But given this yay decoupling, which all of us already enjoy today, pretty much, the holy grail of compute storage separation is actually being able to scale them independently. So storage solutions today are very scalable, like everything from Linux operating system to OBS, NetApp. If you need more space, it's not that hard to get more space. But compute, on the other hand, if you need more compute, you have few options. And again, I'm talking about mostly normal, like basic Postgres that we're all running. You can start getting bigger and bigger machines because things are separate. You can take a bit of downtime, replace the current compute machine with a bigger compute machine. You now have more compute and you can scale up that way. I think people underestimate how far you can go by just getting bigger database machines. But eventually you run out. If you are Twitter, Facebook, these kind of things definitely run out. Even normal companies tend to run out. And then what do? Well, most companies would start sharding. Most databases, with some exceptions, are not particularly shard aware. So sharding basically means you start slicing your data and putting different parts of your data on different databases. And then you have to write your own logic to manage all those shards and where to find your data. Where can your application find your data? You need some kind of a layer for that. So in order to build something better, build something that is far more elastic, the first and critical step is to separate compute and storage. And then you go from there. And in truly elastic database, and there are not that many of them out there in the world, to be honest, but in an ideally truly elastic database, what you really want is to be able to scale by just adding more and more machines and kind of doing it dynamically, take away machines if you don't need them anymore. Just scale the compute as your workload grows or shrinks. And you want it to be very transparent, obviously, both not to do a lot of work yourself and also not to distract your customers. And if storage and compute were still tightly coupled, you couldn't really do it, right? Because the moment you brought up a new machine, you need to start copying data over. Copying data over is anything except quick, dynamic, and transparent. You can do some stuff to make it better, but honestly, not that much. If storage and compute are separate, then you can start thinking about kind of hydrating with partial data, or actually having two machines connect to the actual same storage server and having the database be smart about managing access. You suddenly have a lot more options. So the separation is absolutely critical for having a good solution. And the thing is that the moment you have this solution, which is, again, kind of difficult, not a lot of relational databases are actually there. The moment you have this, and you can really scale almost transparently, minimal overhead, minimal data movement, you can scale your compute and storage separately, it means that adding capacity is something you can do really quickly when you detect that load's going up, even in an emergency if needed. And if you can do it quickly when load's going up, it means you don't have to do capacity planning, saved you a bunch of work. It means you don't have to run with a bunch of extra sparse capacity just in case load starts rising and you need something to tide you over. So less work, less money essentially wasted. Definitely a really good thing to have if the system is designed for that. And of course, because compute and storage are separate and you have the ability to scale each one of them independently, it means that you can resolve bottlenecks where they're needed. If you need more compute, you add more compute. You need more storage, you add more storage. You don't need to add things that have X compute and Y storage, even though I only need compute, I never needed that storage. This is another place where we save you a bunch of money. So hopefully at this point, I convinced you that separating compute and storage is a really, really good thing. It's a good thing in the simplest forms that we're all enjoying today. And it's a first step toward doing really amazing things. But now, what about predicate pushdown? Can we really do predicate pushdown, or as Gunnar said, maybe it's an opposing pattern? So let's talk about the simple form of storage compute. Imagine that you have a single database Postgres machine. Files are on a storage cluster. Imagine something like EBS to make it concrete. We already said that storage clusters have compute, right? And they use it for stuff like encryption, compression, snapshots, etc. Now, if you have a very general purpose storage like EBS, this is pretty much all you can do. You can only do general purpose storage stuff. But what if your database had a storage cluster that was actually specifically designed for the database? It was actually aware of relational model, queries, like things. It had a protocol that the database could actually ask the compute to do a bit extra, and the compute could actually do a bit extra. This is pretty much what AWS Aurora did. So you can look up at the AWS Aurora paper. And if you need to make compute and storage through Elastic, you pretty much have to make the storage already have some enough logic so you can actually add more compute and not have everything blow up. But you can take it further, and you can say something like each storage node has some of my data, not all of it. What could you do if you have a CPU and a subset of your data and the database who can tell it what to do? What can you do with that? And it turns out that you can do quite a bit. So if you're familiar with the MapReduce model, anything that you can do in a map, you can push down to the storage essentially, because if you remember everything you can do in a map, it can happen on tiny pieces of data and scale out as much as you need. So things like filtering specific records, masking sensitive fields, some formatting, all those kind of things you can push down to the storage in theory. But it turns out that one of those things is much more important than the others. Filtering is much more powerful than anything else you can push down to the storage, pretty much, except some kinds of aggregations, which are a bit harder. Why is filtering so much more important? Because we separated compute and storage. We have a network in between. It turns out that this network commonly becomes a bottleneck, essentially. Like you can scale storage as much as you want, you can scale compute as much as you want, and eventually, with everyone talking to everyone else, this in-between layer actually becomes an issue. And once it becomes an issue, it's actually really hard to solve it, because you cannot solve it by adding more compute. You cannot solve it by adding more storage. What do we actually do? Well, the only solution is to start sharding the database in order to limit the cross-node traffic in different ways, which is, again, as we said, sharding is not what we want to do. So this bottleneck is a problem that was created by the compute storage separation. If I'm running this one machine, it's very rare that I don't have enough bandwidth between my CPU and the disk. It could happen, like the CPU south bridge, north bridge kind of stuff can run out of capacity. Extremely rare. In separate machines, obviously the network is a lot more complex and bottlenecks pop up a lot more. So the way to solve it is what's called predicate pushdown. You take the predicate in a query, which is essentially the where clause, and you send it over to the storage device. Each storage node gets all those conditions, where X equals Y, this thing equals that thing, and starts filtering the data. And it only sends back to the compute layer the rows that actually match the filter, which is usually a tiny subset of what it actually has to read in order to figure out which rows are the right ones. Remember that you are also saving on indexes, like all those things. And in all TP systems, it's really sometimes makes a difference between I'm sending up the network 20 gigabytes and I'm sending up the network 1 kilobyte. It can be extremely meaningful. And the thing I love most about the idea of applying predicate pushdown in a database where I separated the compute and storage is the fact that I'm using the pros of the system, where I have storage nodes and they have the data and a lot of compute, to solve the drawbacks, the bottlenecks that this design itself created. So it feels like a bit of a ninja move where I'm using the pros of the system to counteract the negatives, kind of thing. I really, really love this in general. And key thing to remember, I talked about how cool it is in compute storage databasing, but predicate pushdown is useful in so many different systems. It's one of those core design patterns, if you are preparing for a design interview, like it's one of those really basic things. So you can apply it between the front end and the back end. You can apply it between a service and its database. You can apply it between two different microservices. The key to this is that you need to have an API or a protocol that allows you to send filters to the place where the data is. So, the front end needs some data from the back end. If it knows that it's going to need to filter them because the user clicked on the right things, can it send those filters down to the back end? So less data will go over the network back to the front end. If the back end has to call a different service, again, can it actually send those filters again? That back end has to call a database. Definitely make these filters part of your query so you don't have to read rows from the database. And hopefully your database will send some of those filters down to the storage layer, so you will never even have to get this data to the database. It's turtles, or in this case, predicate pushdown, literally all the way down. And it's a really cool, like you basically, if you want to think this way, you can create a far more scalable and far faster systems. So definitely keep this in mind in your designs, regardless of whether you're building databases or something a bit more standard like the rest of us. So hopefully you learned a bunch of things about how separating compute and storage can mean different things to different people. Why storage, no matter what you do with it, it will still have some compute attached to it. And why storage and compute separation, it's not just that it doesn't conflict with predicate pushdown, they're actually much better together. They're such great complementary. So I hope you enjoyed this show. I'll see you again in 2 weeks, and Happy New Year, everyone.